Swayam Prabha. Digital India. Educated India.
So now we are going to move to further higher dimension. So we started with single random variable, then we talked about vector random variables, then we are going to talk about three dimension already covered, right? Like vector means, yeah, up to m dimension is covered. Now we will talk about infinite dimension. It is like I have collection of uncountably many random variables. Okay, and so you will see that in most of the application that is what it's going to matter to you, because you want to understand like how the, suppose for example you want to understand how the stock market is evolving, right? You will be not interested in one day, you will be interested in how it performed in the last 5 years and how it is going to evolve in the near future. So you have the collection of random variables which need not be some finite number there, it could be uncountably many. And if you are trying to like find a trajectory of a particle or whatever, at every point of time you want to understand how that is behaving, right? And there are so many such times. So suppose let's say something is taking a trajectory, and at every time you want to, every time its behavior you are trying to control, but its behavior could be random at that point, right? Depending on so many others. Now you want to understand at every time instance you want to model it as a random variable. So we will try to make this more precise. So that will lead us to something called random processes. So here earlier also when we talked about random vectors, we had collection of, let's say, finite number of random variables, but here that need not be the case. Here the indexing set T could be uncountable, countable, but it could be infinity. So, and if in this case, if this T happens to be, let's say, integers. When I say integers, let's say it is going to be like 0, 1, 2, 3, 4 all the way like that. Then we are going to say that then this random variable x is called discrete random variable. And if this T is going to be, let's say, a real line or some continuous interval, then x is called discrete random process.
The collection of random variables x1, x2, x3.
Right.
Then how t can be real? Integers only, x1, x2.
So it could be just like a time in the interval 0, 1. You take any point in the interval 0, 1, there is a associated random variable. So for example, as I said, right, if in the stock example case you said, we took xt could be the value of the, what is that, our stock BSE stock index, whatever, let's say on every day. So on every day you can count, right, day 1, day 2 like this, and its value xt is going to be random. We can't predict a priori what is that value, right? So that will be denoted by these xt's. If you give me a day, xt will tell, xt is the random variable associated with that day.
That is discrete random process.
That is discrete random process. But suppose you want to understand, let's say, for example, let's say you are moving in a vehicle and you are trying to accelerate your vehicle, but you are in a very uncertain environment, right? At every point, the velocity that your vehicle is attained could be a random variable. So in that case, at every possible time, in the time of interest, you want to understand what is the velocity at that time. Okay. So for example, let's say I have interested in 1 hour of time. Okay, this could be all possible seconds from 0 to all possible minutes from 0 to 60 minutes. And you can think of anything like either vehicle moving or I am heating some object and I want to understand the temperature profile in that. At every moment you want to understand like what is the velocity or the temperature profile of that. So in this case you can more that t here could be all possible values between 0 to 60, right? Every instant you are talking about. Okay, so then in that case we are going to look it as a continuous random process. So most of the times we will be dealing with discrete random process, but you will also encounter many examples in real life where one has to worry about the continuous random process also. Okay, now we can interpret my random process in different possible ways. Suppose a random process I have like this. Now one possible way to interpret is, as we already said, we can say that for all t in t, xt is a function from omega to r. This is just a random variable, right? So these are collection of random variables. So for every t, this is like a random variable which is giving value to each of my elements in my sample space. Alternatively, we can think it as this entire x itself is a function on so where it is going to give the value where for all t and omega in t comma y, x t of omega is the value of sample omega at time t, at index t. Okay, so you can think of this x to be now like this is random variable, right? So now it has, you can think of it as 2 dimension to this. One is the index and another is given that index, what is the value it is going to take on a given sample. So for x, that is why we are saying it is indexed as well as what is the value it is going to take on a sample. If you tell, okay, x is collection of my, is a random process corresponding to, let's say, behavior of my stock exchange or what is the index on a particular day. If I say on day 10th about this particular sample, what is the outcome, then this x is going to give this. If you have to look at on that particular day, on the particular sample, what is the value it took, and this is how we can interpret this random process as. Other way we can think about is, so this is like fixing t. You fix a time and then look at on that particular day how this value is going to change for each of the sample, what are the possible values for each of the samples. Or you can fix omega, a sample, and then look at on this sample how the value, possible values on each of the days. Okay, so for example, let's say you are interested in some 10 shares in the market, whatever that companies are, and you have a random variable which assigns for each of the shares whether it made a positive gain or a negative gain, right? Now you can think of on a given day what is the outcome for each of my shares. So shares is a collection of this sample space, right? What is the value it took? Alternatively, you can, what you do, you can focus on a particular share and then look at on different days what it took, what is the value it took, right? Now you can think of x of t as a function in t, and to call xt omega as sample path corresponding to omega. For example, let's say I have this. This is my time index, and I am interested in knowing my x of omega of a particular sample. So this sample may take value like this. I don't know, it's not. It may fall, it may rise, it may fall like this, right? And this is going to be, this I'm going to just interpret as x of omega. So as for different value of t, it is going to give me what is the value taken on that sample omega here, okay, and this is, we are going to call it as sample path. So is this different interpretation clear? So okay, let's now rework them. If I am going to fix an omega and then I am going to see like as a function of t how it behaves. So this is like I have done it for a continuous case. If it is discrete, I will have only certain points here because this t only takes some values, right? Now you are going to look into like as this aspect. What you do in this case, if you want to draw this, you are going to fix time and these are your omegas. This could be, let's say, omega 1, omega 2, all the way up to like you had some n points, and what is the value taken. Let's say this is some value, here is some value and this is some value. So this is like a single random variable, right, at a given time t, and here it is given sample, how it behaves at different points of time or a different index. And here either you can now look it into in the joint space of this and this given at omega. So for each omega I can vary this t and get this graph. Okay, so if you give me a t and an omega, then I will come up with a particular point. So suppose you give me some omega, let's say you give me omega 2 and you also give me t equals to 10. I will look at this graph for t equals to 10 and then I get the value, right. So and that second interpretation will just give you that. Okay, fine. So then we have, so just an example. Suppose I have this W1, W2 are independent random variables. Such that let xn equals to summation k equals to starting from k equals to 1 to let's say n. Omega k. This is for all k. So I am saying I am giving you collection of this random variable, index random variable, index at 1, 2 all the way up to infinity. Is this discrete or continuous random variable here? It is going to be discrete, right, because now I have index which are at discrete points, and now I am saying each of these random variables are independent, and further each one of them is such that it is only going to take two values, 1 and minus 1, and probability that it takes 1 is half. Okay, and now further I am going to define another random variable xn, where for all again let us say 1 to infinity. So this is now sum of these random variables. Is this xn? Now I have these two random variables, one is this w collection of this wk's and another is this x which is collection of this xn. Are both of them are discrete random variables? Yes, right, because anyway w is only defined at 1, 2, 3 index like that, and the xn is also xn is collection of sum of n w's, and that is also defined for each of n integer valued. So this both are discrete random variables. Now let us see how this look like.
W is a random process.
Yeah, it's a random process, right, because each random variable I have defined like this, and it is a collection of so many of such random variables. So now let us understand how this wk of omega looks. For some omega, let us fix an omega, and now let us look it as a function of k, that is in time here. So k is the index. What I am doing is I am fixing a sample point, and for this sample point it may happen that for the first one it could be taking 1, it could be then taking minus 1, then maybe taking minus 1 and then going plus 1 and maybe plus 1 again and like this plus 1. It could be, this is one sample path. So you remember I have defined a sample path here. For this particular random variable I am now trying to draw a sample path. Okay, maybe I don't need k here. So this is like 1, 2, 3, 4, 5, 6, and I can go on. Each of this k, my random variable is such that it is going to take either value 1 or minus 1. Okay, so let's say when I performed my experience, in the first round it took value 1, in the second round it took minus 1, and it again took minus 1, and it took 3 consecutive 1 after that, and something happened subsequently. I don't know what is that. So this is going to give me a sample path of this process for a given omega. Now let's try to draw my sample path for x. Now x is a random process which is a function of w. So if I know this process, should I be also able to draw the sample for this? Okay, maybe. Okay, so let's see what will be the value of x of omega at n equals to 1? It is going to be this. And what will be at 2? It is going to be 0. Then 1. Then 2. Going to be like this, right? So this is how we are going to get some picture of what is going to happen like on a given path. If you look at some fixed sample point, and then we can visualize how on this point my graph is evolving as it takes different values. So as I said, for example, if you are going to focus on a particular share value, you can now look at on each of the days whether it made a positive gains or negative gains and plot it like this. And this could be like the cumulative effect. So the cumulative effect is till date it made effectively positive gain or negative gain. So for example, this curve here could be like on each of the days it is making positive gains or negative gains, and here it could be till this point the cumulative gain is positive or negative. Okay. Okay, then for such random process we are now going to define mu of x of t is going for all t is t . So now I have so many random variables, right? One defined for each of the possible index. Now I am going to define mean for each possible random variable I have. So that I have one random variable for each of the index, right? So for each of the index, the mean value is simply going to be the mean value of that random variable. And this correlation we have, now it depends on which two random variables we are talking about, right? Now suppose if you are talking about random variable at time at index s and t, then you are going to denote, that is now you have to specify which index we are talking about to calculate this correlation. So if you tell me s and t are those indices, then the correlation between that random variable is this. And similarly, covariance of our random variables at indices s and t will be given by covariance of xs and xt. And then the CDF of this random variables and is going to be defined as, now we have to, when I am talking about this random process, I have to tell which random variable I am going to talk about, right? And that is going to be specified by its index. Okay, so suppose if I am looking at distribution of n random variables, then I have to specify at what is the time, what is the index you are looking at them. So you are going to specify those indices, and then if in that case the CDF of this involving n random variables is going to be defined as the random variable at index x of t1 taking value less than or equals to x1, and the random variable at time x2 taking value less than or x2, like this all. Now to give a complete characterization of this random process, you need to define this for all n. N is what? Integer. Okay, and for all x1, x2, xn belonging to Rn, right, because you have now a collection of random variables. To give a complete characterization of this random process, you need to tell me if I am going to look at this set of random variables, what is their distribution, and I should be able to tell this distribution for any possible set of random variable you are going to ask me. Okay, that is why you tell me how many set of random variables you want to look at, and you tell me which are the indices, what is the set of random variable. To decide that, you need to tell me the indices. Okay, and then okay, we have to also tell this. So then for all this, and also t1, t2 all the way up to tn, that is coming from your again t to the power n, because these are this many indices, right? So you have to tell me which are those indices you are looking at and what is the value you want to, and I should be able to tell what is the probability that at that random variable taking value less than this particular number. So I need to specify all of this to completely characterize my random process, and this kind of things, if you can define your this CDF for all possible value of n and for all possible indices and for it taking all possible vector like this, if you, this is called finite dimensional distribution. So see, like random process is a complicated thing, right? There are so many random variables there, and this could be potentially uncountable, but to define it completely, you need to specify how any possible subset of these random variables in this random process are going to behave. If you are going to like if you can't specify the way it behaves at some indices, then you are not completely specifying me your random process. That's why to explicitly completely characterize your random process, you need to define your CDF for all possible subsets, for all possible values it is going to take, and also for all possible indices you have, and that is, so this FDDs is what going to completely characterize your random process. Okay, and now this is the mean function here. I am going to call mu of xt as a mean function for my random process x. Why this is function? So it is now takes input t, right? It is going to change as your indices changes. And this is So this is, we are going to call a correlation function now. Earlier when we had any two random variables, we know how to find their correlation, right? If you give me x and y, expectation of xy is their correlation. But now I have so many of them, not just xy, I have x1, x2 all the way up to infinity. So you just tell me which two random variables you want to look at the correlation, and I am going to compute. So this is going to be a correlation function now. And what is this? It is now a covariance function. So sometimes you may be interested in, you may want to set s equals to t itself, that is looking for a covariance of a random variable with itself. It is going to be variance, but in this parlance you can, if you are looking at the same, you can add auto covariance. So auto I add when I am going to look with the same time index. The time indices are not two different things, same things. Okay.
S is equal to T, then we will call it auto.
Yes. Okay, then we have this definition. So if my random process is such that each of the component in this process has a finite second moment, then I am going to call it as a second order random process. Okay, so this is just our definition. So just one point I want to add here. So this is, this is a CDF, right, which I have defined for all possible subset. If I know that my process is, my random variables are all discrete, right, maybe then I may be interested in only probability mass function equivalent of this. For example, if I have all my random variables are discrete, then instead of looking for the CDF, I may be just interested in x1 t1 all the way up to xn tn to be just equals to probability that x of t1 equals to x1, x of t2 equals to x2, all the way up to x of tn equals to xn. So this is just like a probability mass function version if my random variables are all discrete. So I am talking about two discrete things here. My random variable itself taking discrete values, and then the indices being discrete, right? So my process is discrete random process if my time index is discrete. Further, if each of my random variable is such that it only takes value from a discrete values, then I'll be interested in only further this probability mass function in that case. Okay, because this gives all the information. I don't need to go for this complicated CDF in that case. Okay. And similarly, we are also going to say that my set of any n set like this are going to be continuous here, jointly continuous if they have a corresponding PDF, the way we did earlier, right, for a single random variable. If I can find if I am able to express this in terms of some function f of small f of xn in terms of the integration way we did earlier, then I am going to say this set of random variables are continuous. Okay, so we will just the nth order PDF. That is okay, this is just like completeness. Okay, now I want to Okay, just let me complete this one more time, then we will move to the next class. So further we will study some more properties of this in the next class. Let's stationarity and wide sense stationarity. So before that I want to just tell you what I mean by a Gaussian random process. Okay, I have talked about what is a Gaussian random vector, but now I have defined a Gaussian process. Then you may want to specify what we mean by a Gaussian process, right? A random process So now we are simply extending the definition of Gaussianity from random vector to random process by saying that we have in the random process we have so many index random variable, but from this index random variable, if any linear combination, if the random variables is comprised of S are jointly Gaussian, that means if you take any linear combination of this random variable, if they happens to be Gaussian, then we are going to call this process as simply Gaussian random process. And so we already know that for this in the random vector case, right, we denoted that Gaussian random vector as nu mu k, and its PDF there depended only on mu and covariance k, right. So to define this Gaussian random vector, I just needed to know the mean vector and the covariance vector. Now what do you think I should know to define this Gaussian process? So again, maybe I just need to know what is the means for each t and maybe the covariance for each possible time index pair, right. So for this, so the good thing about the Gaussian vector was it was parameterized, but the parameters were just like the mean value and the covariance value. Now to define a Gaussian random process completely, so that I don't need to really look for all these finite dimensional distributions. So maybe the parameters are just sufficient. So what are those parameters I should be interested in to completely define a Gaussian random process? So maybe one thing is you going to do this mu of xt for all t, and then so maybe like we can just say that if you are going to like take any subset t1 of this time indices, to define this joint distributions, what all the things you need to know? You just need to know their mean vectors and their covariance matrix, which is so as I said, to completely define a random process, I need to define my finite dimensional distributions, right. So for the Gaussian process, what is this finite dimensional distributions? I know that if I take any n, that will be jointly Gaussian, right? For a Gaussian random process. To define that joint random process, all I need is the mean vector and the corresponding covariance function, and the covariance function can be expressed simply in terms of my correlation function and the mean value. So as long as you give me the mean vectors, as long as the correlation function, I have the complete information about the finite dimensional distribution of my Gaussian random process, because I know how to construct my probability density function for each of these n, and I can do it for any possible n. So is this fine? So if you have a Gaussian random process, its characterization much simpler. All I need to know is its mean vectors and its correlation function. But if it's not a Gaussian vector, maybe things are a bit more complicated. I have to define finite dimensional distribution for all possible n. Okay, so let's stop here then.